Aaron, here's essay 3 or exam 3, essay 2. Today we're talking about pressure volume loops. So on this side we have pressure, on this side we have volume. Kind of looks something like this. So right here in our graph, what's happening is the bicuspid valve or the mitral valve is opening, which begins diastole. Well, it doesn't begin diastole, but it opens the bicuspid valve and blood starts to flow into the heart. Here, the bicuspid valve is going to close, so we'll have our atrial contraction here towards the end. When this happens, the ventricle starts to contract. So this is isovolumetric contraction. Isovolumetric contraction is going to occur until we reach this point, which is called afterload. And when this point is reached, the aortic valve or the semilunar valve is going to open. Blood is going to flow into the aorta until it reaches a certain pressure point where the AV valve closes. I guess let's call it the aortic valve. Just to be clear, aortic. So then when that occurs, at the closing of the semilunar valve, we're going to have volumetric relaxation. So pressure and volume, this repeats over and over again for every contraction of the heart. But this tells us some important things. This spot here is called preload. It's also called end diastolic pressure. So diastole starts here, goes to here, and all the way over. End diastolic pressure is how much pressure and how much volume is at this point right here. So at preload determines how much the heart's going to pump out. If we increase preload, we're going to increase what we call the SB. Or the systolic volume. No. I'm so sorry. It's called the stroke volume. Whatever. Sorry, I forgot that word real fast. I just wanted to look it up. So the stroke volume, preload determines mainly the stroke volume. Then up here we have the afterload. And this is how much pressure is needed to open the valve, to open the aortic semilunar valve. So what happens here is if we have an increase in vasoconstriction, it's going to increase pressure in the aortic tree, the arterial tree, which means that there's going to be a higher afterload, or a lower afterload would be because of vasoconstriction in the arterial tree. So that's mainly what's going to be happening here. And so inotropy, if you put a little 0 down here, this is what the volume would be if the pressure was 0. We can draw this line between here. We call it inotropy. So inotropy is going to measure for us the contractility of the heart, how hard the heart is pumping. And so we can adjust that through sympathetic signals, through beta-1 receptors. So if we choose to increase the inotropy, what's going to happen is It's going to increase stroke volume, as well as it's going to increase how hard the heart is pumping. So if we decrease inotropy, if we have more parasympathetic systems at play, go same level, we would decrease stroke volume, therefore decreasing the slope of inotropy. So then we can also talk about afterload. So if we increase afterload, we're increasing arterial pressure. If we decrease, what's going to happen is we're going to... So oftentimes it will maintain the same inotropy, which therefore either decreases or increases stroke volume. So if we have an increase in afterload, we're going to be looking at, an increase in afterload, we're going to be looking at the same inotropy, which means our stroke volume is getting smaller. So it requires more to push blood out of the heart, so the heart is going to pump out less per pump. And then if we have a decrease in afterload, it's easier to open the valve, which can be caused by vasodilation. Then our SV gets larger as it reaches the inotropy lower down on the same slope, the line. So it increases stroke volume, so the heart can pump more per pump. And then the very last one we want to talk about is preload. Preload can be increased by venous return. So as you do exercise, or if there's a vasoconstriction, it increases venous return, then preload is going to increase. So in this case, preload is going to come out here more. This is going to increase stroke volume. And then we're going to have overall a larger arc. We can also decrease preload, right? If we decrease venous return, if that happens, it's a decrease in stroke volume. And if you notice, our afterload isn't going to change here, just the preload, which causes a change in stroke volume. So both of those are very big deal. We also have something down here. This can show us what's called compliance. So compliance is how easy it is for blood to move into the ventricle during diastole. So if we have a less steep line, that means it's more compliant, versus if we have a more steep line, then it's less compliant. So an increase in compliance means the heart is not as elastic. So we have another term, elastance, which is measured pressure, change in pressure per change in volume. And elastance tells us how stiff is the heart. If there's an increase in elastance, it's a stiffer heart, right? Because it requires more pressure to increase the volume. So next we're going to move on to what's known as baroreceptors. So baroreceptors, let's draw our heart. So baroreceptors are stretch receptors on the aorta, as well as on the carotid sinus in our neck. So I'll just draw a vessel like this. That can represent our carotid sinus. Let me redraw this a little. Let's draw... So what's going to happen here is these receptors here, they sense stretch. So as they stretch, they're going to send signals to the brain, which is going to tell it to decrease blood pressure. However, if they're not stretched enough, So decrease in stretch, increase sympathetic. But increase in stretch is going to be an increase in parasympathetic, right? Because parasympathetic is going to cause the heart to relax. So it's going to send afferent pathways. So this is cranial nerve 10, and then this is cranial nerve 9. And so that's our afferent pathway, which is going to go back to the brain. Then the brain is going to process it, and we have two options. We'll say this is the sympathetic option, as well as this can go to the adrenal medulla. It can also go to vessels. So what's going to happen is, this is the control center here. It's going to send an efferent signal down to our effectors. So our effectors here, can be the adrenal medulla, which is going to release norepinephrine or epinephrine, which is going to cause blood pressure to increase through increased heart rate, right? We can also cause vasoconstriction through alpha-1 receptors. This is going to cause increase in venous return, which will also increase blood pressure. Then the sympathetics right here, this is gonna beta 1, so this could have inotropic, chronotropic, or lusotropic effects, right? So it's gonna release more calcium, it's gonna increase contractility, or it could increase the rate at which this is. So this is heart rate. Or lusotropic, it could decrease the time in between relaxation. This is going to increase pressure. So this is only going to happen if there's less stretch. If not, we're going to get a parasympathetic change. So it's going to come back down, cranial nerve number 9, and it's going to send signals to M2 receptors, which is going to decrease chronotropy. So this is the baroreceptors and how it works. So let's talk about MAP, or mean arterial pressure. So mean arterial pressure, in this case, we're going to take our average from diastole and systole, and we're gonna give it a line. So the mean arterial pressure changes from our heart or large vessels to our veins. So in the middle is going to be capillaries. We could say these are arteries. So mean arterial pressure can equal diastolic pressure, we'll simplify it, and diastolic pressure plus 1/3 the difference between end systolic pressure and diastolic pressure. So if we actually scroll back up here on this graph, let me clean it up a little bit, we can see end diastolic pressure and systolic pressure. The difference here is going to be our mean arterial pressure, or this part of the mean arterial pressure. So mean arterial pressure is also affected by the slope or flow of blood. So our flow of blood is equal to the change in pressure times pi times r to the 4 over 8 VL. So this is viscosity, and this is length. So this is a way of showing peripheral resistance down here. So peripheral resistance affects mean arterial pressure. If peripheral resistance increases, MAP is going to decrease. If peripheral resistance increases or decreases, then MAP will increase. So what's really important here with this is the radius. So vasoconstriction and vasodilation are super important in order to regulate MAP, because since it's r to the 4th, small changes make a big change in the flow of blood, which means a big change in the mean arterial pressure. So the very last thing we need to talk about in this video is I need to explain capillary exchange. So we start on this end, we have our artery, or arterial, because arterioles are the smallest arteries, and then we have our venules. Smallest form of our vein. This here is a capillary. So what's happening is we have these endothelial cells that interact with what's known as the interstitial space. So this is the space between that and tissue cells. So this is tissue. So we're going to have several forces involved here that are going to allow and move fluid in and out of the capillary. So this is how fluid as well as nutrients are passed through. So the first one we're going to talk about is hydrostatic. Hydrostatic pressure. This is basically the pressure that's here, or referred to or affected highly by blood pressure. So hydrostatic pressure is going to push fluid out. Now, I typically say it has a pressure of about 30 millimeters of mercury. Well, our interstitial space fluid is also our interstitial fluid pressure, whatever. IFP is also going to cause a pressure to come in. This is referred to as a -3 pressure, milligrams of mercury. The 3 is trying to tell us that it's suction, so it's pulling out of the cell. Then we have 2 other forces, and these are based off of proteins. So inside capillaries, we have large proteins, also referred to as colloids, which can't pass through the gaps in between the endothelial cells. The biggest one is albumin. So what's happening here is there's something called BCOP, which is blood colloid osmotic pressure. And so since these albumin are here, it's going to cause an inward pressure of about 28 milligram of mercury, millimoles, whatever, the pressure unit. And then we're also going to get what's called ICOP. Now this is interstitial colloid osmotic pressure. So we also have proteins out here, which is going to bring out a force of about 8 millimoles of mercury, micrometers of mercury pressure. And so what's going to happen is all these things total are going to create net pressure. So on the arterial side, If you add up out and in, going in we have 28 millimoles millimeters of mercury. Going in we have 30 millimeters of mercury. We have 8 millimeters of mercury, and we have 3 millimoles of mercury. Right, so then if we add these all together, we get 41 and 28. So if you subtract the two, you get 13 millimoles of mercury pushing out. So more fluid is going to come out. As we get towards the Venus side over here, what's going to happen is we're going to get a change in the hydrostatic pressure. So IFP is the same, it's going to be 3. BCOP and ICOP are still 8 and 28. BCOP and ICOP. The hydrostatic pressure is going to be decreased. So what's going to happen here is we're going to have our out and our in. This is going to be 28 millimoles of mercury. We're going to have our 8 from ICOP. We're going to have our 3 millimeters of mercury from IFP, and then we're going to get 10 millimoles of mercury from the hydrostatic pressure. So once we add all this up again, we get 28 and we get 21, which is gonna 7 millimoles of mercury inward. So the idea is that goes out, then comes back in, but as you notice, this is a greater number than this one. So what's going to happen is our lymphatic system will absorb excess amounts of fluid and therefore cause this to work properly. So something can happen which causes problems here, and it's called edema. Edema is swelling or an increase in interstitial fluid. So something that can happen, just to give an example, so if a mast cell releases something called histamine, there's drawn red, it causes these to have a gap between them. When that gap forms, albumin can come in and pass through to the other side. So what's going to happen here is this going to decrease BCOP. So if BCOP decreases, we're going to get edema, right? Because if we have less than 28 here, this is going to be a bigger number. This is going to increase. So edema is when there's increase in interstitial fluid. So there's a good example of when histamine can cause edema. What happens is we give them an antihistamine, which is going to bind to the histamine, causing it to stop, which will return this to normal. Something else that can happen, another example of edema, is if the right side of the heart, right side heart failure. So if the right side of the heart isn't working properly, it's not able to pump all the blood, it's going to increase venous pressure. If we get an increase in pressure over here, that is going to increase our hydrostatic pressure. If we get an increase in hydrostatic pressure, more fluid is going to move out. Increase in hydrostatic pressure, which is going to cause an increase in fluid leaving, which is going to cause edema. So there's a couple of examples of edema, and hopefully that works for you. Thanks, Aaron.